The roots of modern mathematics lie in figures that, more than 2 millennia ago, dared to systematize geometric knowledge. Among them, Apollonius of Perga stands out, whose work, the Conics, not only classified the fundamental curves of geometry, but also paved the way for advances in astronomy and physics. In this video, we will investigate the trajectory of Apollonius, his origins, his writings, the critical fortune of his work, and the role of his ideas in the mathematical tradition that has come down to us. It is a journey that takes us from the Hellenistic world to modern scientific thought.
The greatest mathematicians of all time. Episode 10. Apollonius of Perga. Apollonius Pergaeus, called the Greek Geometer, is sometimes considered the second greatest mathematician of ancient Greece. Euclid, Eudoxus, and Archytas are other candidates for this honor. His writings on conic sections have been studied well into modern times. He developed methods for normals and curvature. He deliberately emphasized the beauty of pure rather than applied mathematics, stating that his theorems were worthy of acceptance for the sake of the proofs themselves. The following generalization of the Pythagorean theorem, where m is the midpoint of BC, is called Apollonius's theorem. Apollonius of Perga was born about 262 BC in Perga, Pamphylia, Greek Ionia, now Myrtina, Antalya, Turkey, and died about 190 BC in Alexandria, Egypt. He was known as the Great Geometer. Little is known about his life, but his works had a great influence on the development of mathematics. Apollonius of Perga should not be confused with other Greek scholars named Apollonius, as he was a common name. For example, Apollonius of Rhodes, born around 295 BC, a Greek poet and grammarian, a pupil of Callimachus, who was a teacher of Eratosthenes. Apollonius of Tralles, 2nd century BC, a Greek sculptor. Apollonius the Athenian, 1st century BC, a sculptor. And Apollonius Discalus, 2nd century AD, a Greek grammarian who was considered the founder of the systematic study of grammar. And Apollonius of Tyre, who was a literary character.
Perga was a cultural center at that time and was the place of worship of Queen Artemis, a goddess of nature. As a young man, Apollonius went to Alexandria, where he studied with the followers of Euclid and later taught there. Apollonius visited Pergamum, where a university and library similar to those in Alexandria had been built. Pergamum, now the city of Bergama in the province of Smyrna, Turkey, was an ancient Greek city in Mysia. It was situated 25 kilometers from the Aegean Sea, on a hill on the north side of the wide valley of the Caicus River, called today the Bakir River. While Apollonius was in Pergamum, he met Eudemus of Pergamon, not to be confused with Eudemus of Rhodes, who wrote the history of geometry, and also Attalus, who many think was King Attalus I of Pergamum. In the preface to the second edition of Conics, Apollonius addressed Eudemus. If you're in good health and things are, in other respects, as you want them to be, that's fine. With me, too, things are moderately good. During the time I spent with you in Pergamum, I observed your eagerness to become acquainted with my work on conics.
The only other information about Apollonius' life can be found in the prefaces to several books by Conics. We learn that he had a son also named Apollonius, and indeed his son took the second edition of Book 2 of Conics of Alexandria to Eudemus in Pergamum.
We also learn from the preface to this book that Apollonius introduced the geometer Philonides to Eudemus while they were in Ephesus. We are in a slightly better state of knowledge about the books that Apollonius wrote. Conics was written in 8 books, but only the first 4 have survived in Greek. In Arabic, however, the first 7 of the 8 books of Conics survive. First, we should note that the conic sections for Apollonius are, by definition, the curves formed when a plane intersects the surface of a cone. Apollonius explains in his preface how he came to write his famous work Conics. I undertook the investigation of this subject at the request of the geometer Naucrates, at the time when he came to Alexandria and stayed with me, and when I collected it into 8 books, I delivered them to him immediately, in great haste, because he was about to embark. Therefore, they had not been completely revised. In fact, I had written everything exactly as it occurred to me, postponing the revision until the end. Books 1 and 2 of the Conics began to circulate in the form of their first draft. In fact, there is some evidence that certain translations that have come down to us came from these early drafts. Apollonius writes, "It happened that some people also, among those I knew, received the first and second books before they were corrected."
Conics consisted of 8 books. Books 1 through 4 constitute an elementary introduction to the basic properties of conics. Most of the results in these books were known to Euclid, Aristeas, and others, but some are, in Apollonius's own words, elaborated more fully and generally than in the writings of others.
In Book 1, the relations satisfied by the diameters and tangents of the conics are studied, while in Book 2, Apollonius investigates how hyperbolas are related to their asymptotes, and also studies how to trace tangents to given conics. There are, however, new results in these books, in particular in Book 3. Apollonius writes about Book 3, "The most beautiful and important of these theorems are new, and it was his discovery that made me realize that Euclid did not elaborate the syntheses of the geometrical place in relation to 3 and 4 lines, but only a part of them, and without success. For it would not be possible for the said synthesis to be completed without the aid of the additional theorems discovered by me." Books 5 through 7 are highly original. In them, Apollonius discusses normals to conics and shows how many of them can be traced from a point. He presents propositions that determine the center of curvature, which immediately leads to the Cartesian equation of evolute. English mathematician and historian Thomas Heath writes, "Book 5 is the most remarkable of the books in existence. It deals with normals to conical lines, considered as maximum and minimum lines drawn from specific points to the curve. It includes a series of propositions which, although elaborated by the purest geometrical methods, actually lead immediately to the determination of the evolute of each of the 3 conics. That is, the Cartesian equations of the evolutes can be easily deduced from the results obtained by Apollonius. There is no doubt that the book is almost entirely original and is a true geometric tour de force. The beauty of Apollonius's conics can be easily seen by reading the propositions given by Heath. However, Heath explains that it is very difficult to read the original text. The treatise is a great classic, which deserves to be better known than it is. What prevents its reading in its original form is the great length of the exposition. It contains 387 separate propositions, due partly to the Greek habit of proving particular cases of a general proposition separately from the proposition itself, but more to the complexity of the enunciations of complicated propositions in general terms, without the aid of letters to denote particular points, and to the complexity of the Euclidean form to which Apollonius adheres from beginning to end.
The Greek geometer Pappus, who lived at the same time, gives some indications of the contents of 6 other works of Apollonius. These are cut of a ratio in 2 books, section of an area in 2 books, overdetermined section in 2 books, tangents in 2 books, flat places in 2 books, and on virgin constructions in 2 books. Cut of a reason survives in Arabic, and we are told by the 10th century bibliographer Ibn al-Nadim that 3 other works have been translated into Arabic, but none of them survive. To illustrate how far Apollonius took geometric constructions beyond those of Euclid's Elements, we consider results that are known to have been contained in tangents. In Book 3 of the Elements, Euclid shows how to draw a circle through 3 given points. It also shows you how to draw a tangent to 3 given lines. In Tangentius, Apollonius shows how to construct the circle that is tangent to 3 given circles. More generally, it shows you how to construct the circle that is tangent to any 3 objects, where the objects are points, lines, or circles. The Dutch historian John Peter Hogendijk reports that 2 works by Apollonius, which were previously not thought to have been translated into Arabic, were in fact known to Muslim geometers in the 10th century. These are the works Plane Loci and On Verging Constructions. Some results of these works that were not previously known to have been proved by Apollonius are described. From other sources, there are references to still other books by Apollonius, none of which have survived. Hypesicles refers to a work by Apollonius comparing a dodecahedron and an isocohedron inscribed on the same sphere, which, like conics, appeared in 2 editions. Marinus, writing a commentary on Euclid's data, refers to a general work by Apollonius in which the fundamentals of mathematics, such as the meaning of axioms and definitions, are discussed. Apollonius also wrote a work on the cylindrical helix and another on irrational numbers, mentioned by Proclus.
Eutychius refers to a book, Rapid Delivery, by Apollonius, in which he obtained an approximation to pi better than Archimedes' approximation. In On the Burning Mirror, Apollonius showed that parallel rays of light are not focused by a spherical mirror, as previously thought, and discussed the focal properties of a parabolic mirror. Apollonius was also an important founder of Greek mathematical astronomy, which used geometric models to explain planetary theory. Although astronomers eventually concluded that it was not physically correct, Apollonius developed the epicycle and deferent model of planetary orbits and proved important theorems in this area. Ptolemy, in his book Syntax, says that Apollonius introduced systems of eccentric and epicyclic motion to explain the apparent motion of the planets in the sky. This is not strictly true, since the theory of epicycles certainly predates Apollonius. However, Apollonius made substantial contributions, particularly using his great geometrical skills. In particular, he made a study of the points where a planet appears stationary, i.e., the points where the forward motion changes to a retrograde motion or the reverse. There were also applications made by Apollonius using his knowledge of conics to practical problems. He developed the hemicyclium, a sundial that has the hour lines drawn on the surface of a conical section, providing greater accuracy.
Apollonius formulated several problems, the most famous being Apollonius's problem, which consists of finding a circle tangent to 3 objects, the objects being points, lines, or circles, in any combination. Building the 8 circles, each tangent to 3 other circles, is especially challenging, but finding only the 2 circles containing 2 given points and tangents to a given line is a serious challenge. Wied was famous for discovering methods for all 10 cases of this problem. Other great mathematicians who have had fun reconstructing Apollonius's lost theorems include Fermat, Pascal, Newton, Euler, Poncelet, and Gauss. In assessing the genius of the ancient Greeks, it is well to remember that their achievements were achieved without the convenience of modern notation. It is clear from his writings that Apollonius almost developed Descartes' analytic geometry,
but failed due to the lack of elementary concepts such as negative numbers. Leibniz wrote, "He who understands Archimedes and Apollonius will admire less the achievements of the most outstanding men of later times." There is no reliable information about the cause or circumstance of Apollonius of Perga's death. The study of the work of Apollonius of Perga shows how concepts elaborated in ancient Greece became pillars of diverse areas, from Keplerian astronomy to contemporary mathematics. Even with the loss of a significant part of his treatises, Apollonius's legacy continues to be the object of investigation, critical editing, and philosophical reflection. If this content has contributed to your understanding of the history of mathematics, I invite you to subscribe to the channel, share it with colleagues, and leave your academic perspective in the comments. To what extent can Apollonius's ideas still illuminate our current scientific vision?